Okay, so this is what we did last time. The numerical analysis, not or the word is simulation of a motion under forces. Specifically, the what we actually used was what we actually saw was the where is it? The solar system. Okay, so the explanation, once again, I want to point that out again that this is the pretty much, apart from the actual figuring out the forces, this is the whole thing is right here, that last line. So let me put it this way. Okay, so the one thing maybe was not quite clear is that this is the where does the acceleration comes from? It comes from the previous position, Pn minus 1. Okay, what that formula is unspecified. That is the physics of the problem. Otherwise, so if you have physically found the acceleration, then you find the velocity, and then you find the position. Okay, then you put that dot over there. Okay, knowing that position, you find the acceleration again, compute the whole thing again, put one more dot there. Okay, and that repeated on and on. So it's not really that hard to actually show this thing. Okay, so the solar system, but really we could, I just throwing out the moon. The moon goes to hell pretty quickly. Oops, but you can certainly see the rest of it. Okay, the moon is gone. Now this is the Earth rounding the sun. Okay, if you look carefully, you can see that it is more or less circular, but not perfectly circular, I don't think. So we do know that the trajectory is an ellipse. Okay, so I showed you last time where the physics lies. It lies over here, expressing the acceleration in terms of x double prime, in terms of x prime, well, in addition to x, y, and z. Okay, so the location gives me the acceleration, and then according to this formula, I'm computing a velocity and then acceleration, and keep going. So and that is repeated here. What you see is here repeated. Okay. So as you can see that if you look carefully at the formula at the top, it is actually the x coordinate, the purple one, divided by the distance cubed, okay, which is another way to say that the force is inversely proportional to the square of the distance. Okay, so because that's why you have a cube, because x coordinate appears twice, and that's why you have to divide by the cube. So it works out. I can also show you that over here we have the initial position. So the whatever is in green I can change. I could in red too. I could change also the initial velocity. Let me make a copy of this. Okay, so for example, let me go back. Okay, so this is where we are. You can see the initial location. I could put the initial location elsewhere I want. For example, I could put here 1 instead of 1.5, 1 here and 1 there. Okay. I guess it's not the right about I see put the z here. Okay, so okay, let me try to see. I guess I just don't remember what those coordinates were. Okay. Whatever happened? I thought I went back to the original, but I guess not. Okay, so let me try to do it again. Okay, so the initial position is here, initial velocity there, and then we are doing rotation. It is very simple. If you have more planets, certainly then you'll have to make that block over there, repeat it as many times as block you have. It becomes cumbersome. It's just a demonstration, very simple, of orbits that are ellipses, as we know, even though you can make it more complex. Now, so if this feels like doing physics, then what I want to do with this is something that would be mathematical, more mathematical. How? Well, because it is physics. So this is a trick where I'll just change, with your help, I'll change the physics. Okay, so well, let's hypothetically, for example, suppose Newton was wrong, and the force of the gravitational force was not proportional to the square, but was proportional to the cube, which inversely proportional to the cube. Okay, well, and then we can just see what is this hypothetical universe, what kind of motion we can see. So instead of having 3 over here, I will put 4. Okay, and over here as well. Okay, and over here as well. I'll put it everywhere. So it is a different physics, which is in our universe, or at least in our solar system, it's not gonna produce the same result. Or at least that's my guess, that it's not gonna. Oh, so you think, what do you think has happened? You didn't notice? Okay, let's try again. I'm doing slower. What happened? What?
It went crisp. It's burnt.
Yeah, exactly. It fell on the sun. Okay, so why? Because the inverse, it's now if you're close enough, you cannot easily escape the gravitation of the sun, and you fall on it. On the other hand, if I try and put here instead, once again, I'm going back to my force and changing physics, I'll put 2 here. So the power, when we made the power higher, it falls on the sun. And now what if I make it lower, and I put in these all, I put 2. What do you think is going to happen?
Go flat above it.
Oh, let's see. Yeah, it's almost, as you can see, it's turning almost no attraction. It starts at the vertical direction, and then there is an attraction. It deviates from the straight line, but very slowly, and that's why, even if it might come back at some point to the orbit and within this visible part, but maybe not. So it disappears, and then we can wait. I'll give it a few seconds to see, maybe it will come back, but I doubt it. I think it will just it will start to round it in a very large diameter, and it will never come back. Radius, and it never comes back. Okay, so these are the things that can happen. I could certainly remove the gravitation altogether, and then, well, see the power of mathematics. And then you realize then it will be moving at a straight line. There are no forces. Everything moves on a straight line. Well, this is changing physics, but let's change physics in a kind of more reasonable, but also more dramatic way. Let's forget about gravitation, and let's do a spring. With the same spreadsheet, let's do a spring. So with this formula will have to be changed then in a more dramatic way. So let's think about this for a moment. What would this part B? What should we put here? So let me write first what is that we already had. So the roughly speaking, it was an is equal to, what is it? Some coefficient which I ignore, 1 over xn minus 1 over dn minus 1. This is the distance. Okay, so let's not go into the details. We're changing it. So that's gravitation. Now, what if I want to do instead a spring? Specifically, it's called Hooke's law. Anybody familiar with it? Any idea? Any memories? What?
It was on our second physics exam.
Okay, so and don't remember anything? So it's about forces. So what the force depends on what? Well, I mean, we can probably figure out. I mean, the Hooke's was actually a contemporary of Newton and something of a rival. So obviously he kind of probably lost the rivalry, but apparently still something is left. So I think we can figure it out. At least there's some idea in a more mathematical than physical way. So there is a spring attached to a wall. Okay, an object here. Once again, let's say mass is 1, so we wouldn't have to worry about it. And then what makes it oscillate? We pull. There will be a spring constant, yes. And if we pull it off, what? So suppose it is at rest. There is no, by the way, there is no friction on the floor, and I pull it off the restful position. This is the restful position, and I pull it off in here. So it stretches. The spring stretches. Okay, so a force appears. Yeah. So do you remember any specifics about the strength of the force? Right, that's right. But yeah, that's right. So it depends on the distance from the equilibrium. But specifically, we have to do. You just saw the example. It matters what kind of proportion it is. So it just depends on what is the dependence. So remember the dependence. It's just proportional, proportional to proportionally, without any kind of squares, cube, or anything, directly proportional. And that proportional coefficient is the spring constant. So in other words, the F will be equal to say K times delta X, which is the distance from the equilibrium, delta X. This is delta X. Okay. And what's missing? So we moved our what? Yeah, so how do you take care of it? Negative sign, that's right. So negative sign here. So delta X moved to the right, the force pushes to the left, and vice versa. Okay, so that's pretty much the idea, and this is the our location. I don't know want to put delta X here. I think it is just confusing. X is we just what we do is we are allowed to put the 0 at the equilibrium. So then our location will be just how far delta X, that will be just, or X is just how far we get from the equilibrium, left or right. Okay, and so and then that the formula is much simpler than the gravitational. You just multiply by constant. What that constant is really not important. But we are totally ready to carry it out with our spreadsheet. Okay, so I'm going to edit here. Let me. So I highlight it. As you can see, the distance, we don't care about the distance anymore. So distance is gone. Okay, so look at it. It's almost identical of what we want. There is some constant. By the way, I actually at some point I put an actual real constant there. The spreadsheet that for gravitational force was actually totally practical. It was all the quantities were taken from. I looked it up in Wikipedia, and distances as well as all the velocities and the gravitational constant. So it was a real thing. Okay, so Okay, so that's it. So we have some constant times, what's the blue on the mass, okay, that once again it's a constant, doesn't matter, and it is multiplied by the position. Look at it over there on the right, that little purple square is our position, how far off from the origin we are. Okay, so let's so that's all there is. Okay, let's try if it works. Maybe it's moving too fast. Okay, I got to change the velocity. I got to change the velocity here. So let me put zeros here. Okay. Well, maybe this time it's going to be better. It's not moving. Okay, why is it not moving? Yeah, okay, hold on a second. Okay, it seems to be moving, and at the same time I'm not moving. Okay, well, let me put some so velocity is 0. Why is it okay? Let me change this. Let me put. Hold on a second. So I'll put just a 0 here, so there would be no doubt about. I think I'm just messed up the. Okay, I think it is moving a little bit. You see it? Okay, so. So it's moving but slowly. So to see actually effect of it, I would either increase something or decrease something. Okay, I want to increase I want to increase the pull towards it. So I will then increase the number of let's say G over there, which is kind of small. Okay, so let's make it larger. It is actually a very small number. Okay, so how about I put here just 1? Let's see what happens. Okay, well, I guess it went really fast. Hold on, where's... Okay, here it is. Okay. Why does it disappears? Is it... I guess it's just too fast. Okay. Okay, let's try again. What is so fast with the initial velocities? I think they're the zeros. Initial position is 1.5, 0, 0. Okay, so I got it. These are zeros. So it should work. I don't see why it's not working. And it's not working. Why is it? Okay, let me see again. So the numbers are reasonable. No, it's not. Somehow it becomes really big. Why is it becoming big? So look at this number over here. It just can't be right. So this is 1. Oh, h is very large. I see. The h is the time interval is just too large. So let me put a 1 here again. Okay. What happened? Okay, it fell too fast. Okay. Move. Why is it not moving? The velocity is too small again. This is just too small. Okay. Okay. Oh, right. It's working. You see, it oscillates, and it is very is convincing, right? You see how it starts slow and then it accelerates, right? And it goes fast for the center, which used to be the sun. Of course, there is no sun anymore. It's the same spreadsheet, but they're just moving in a different way. Okay, so but that is one-dimensional thing. I could the one-dimensional along the one-axis. What if I make the velocity in the I think in the y direction, say, so I'll push it upward. I wonder what's going to happen. I think it just disappears too quickly. Okay. Okay. What I'm going to do is something else, something more interesting actually. I'm gonna add the second spring. So there will be spring this way, and there will be a spring, a vertical one. If you can okay. So in other words, I'll have the same formula as here, but with, well, let's say with the same exact formula. So let's move it this way. Okay. So as you can see, why is it? Okay. Let me put it here. 1. So I'm changing. What happened? Why the initial? Why is it? There's some. What did I do wrong with this? Something about the position that is just not right. You don't see. Okay, maybe this way. Okay. Okay. Okay, so there is no oscillation with respect to z or y. So the z position changing and the y position changing, but for some reason, oh, I see. I just messed it up. Okay. The picture itself is just does not collect all the information. So this one, no, it is x and y. See, I highlighted the green one, okay, which is the Earth, or used to be that object at the end of the spring, and you can see the two highlighted numbers, two highlighted cells over there. These are coordinates of x and y. So for some reason, the value of x is just so small that it's not detectable. Okay, so it is actually off the axis, but it's just too small. So let me try to change this one to point 1. No. Okay, 1. Stop it. Why is it the y-axis? Why did it just... I don't get it. Why? Just so number so small. The number is so small. The same numbers, and the number is just so small. Start with 1. Start with 1. Okay, let's start over. There's something messed up here. I have no idea what it is. Okay, so I thought I had it, and now it just merged. Okay, so that is the initial position. Okay, that should work. Maybe. Okay. Okay. 2 springs, and they're pushing in different directions. They're pushing in the same direction. They're pulling towards the origin, unless you pass it, and then they pull in the opposite direction, but still towards the origin. As you can see, it oscillates through the origin. So like I said, it's 2 springs. But what if I change the velocity? So what if I give it a nudge in say the y direction? What if I give it a nudge? Interesting, isn't it? So so you see, I don't applaud the actual. First of all, it looks like it's moving along an ellipse, and so can you explain this? So two formulas, and the thing is that so along the x-coordinate there is a Hooke's law pulling towards there are two forces, horizontal and vertical. Okay, they're identical, but only in the sense if their location is identical. So it will be always if you're to the right of the yellow dot, you're pushed to the left. And if you're to the left, it's pushed to the right. If you're above, you're pushed down, and if you're below, you're pushed up. Okay. So, however, then it means that if there is no you don't have an initial velocity, or then you will be swinging as you saw initially towards the center. Okay, and it will be passing the equilibrium on and on. But if you give it a nudge in a circular direction, off the direction towards the center, then in that direction you're going to start moving. So you're being pulled in that direction, but you're moving in that direction. That is totally the same story as with with gravitation. That's why the Earth does not fall on the sun, because even though there is no other force, the force of the sun is pulling the Earth towards it, but the sun is not falling, and the Earth is not falling on the sun because it's moving so fast in the tangential direction, if you like, that it never falls on it. Okay, so and then it turns out that if you look at the springs, this time we have two springs. You produce the same exact effect, almost, well, exactly the same effect, even though the forces are different. And the main difference actually is, even though it looks like an ellipse, elliptical orbits, right? Is it more? I think it is repeating the same orbit, isn't it? Yeah. So, well, do you know the difference? Why this? If you show it to somebody and tell you, does it look like the solar system, they would say no. You know the difference?
It's not perfectly circular.
No, it is an ellipse. We are moving on elliptic orbits. That goes away to even before Newton. Keplers Law says, first Keplers Law says that we are moving along ellipses. They are very close to, these ellipses are actually close to circles, but it took a few hundred years to actually realize that all of those numbers they are going through, realize that they are so messed up because it's not perfect circles. They are kind of elliptic, even though you look at that orbit, it looks, to a naked eye, I believe it looks like a circle. But when you start measuring, you will notice that it's not. It is an ellipse, but the difference is where is the center? You're rotating here around the center of the ellipse, but
Z.
what?
There's no Z.
No, there is no Z, right? So it is flat. That's another interesting thing about the solar system, that all the planets, or almost all of them, are in the same plane. Nothing really stops it from rotating like this in kind of random way, but they are all in the same plane for whatever reason. And that's what we see here. So a z-axis I intentionally kind of hid. Well, how do you make three-dimensional visualization really with Excel? Probably not. So no, the difference is that the sun is located in the focus, in one of the foci of the ellipse, not in the center. So that's another thing. Kind of not obvious, but once again, Kepler discovered it. And then Newton took the Kepler's law and then came up with his laws of gravitation, as well as laws of physics of his, the three laws of physics. Okay, so that's what it looks like. You can try to if I change the forces slightly, I could probably produce more complicated patterns if these two springs are different. Say, how about I put a 2 here? Okay. Let's see what happens. Interesting. You see? the regularity disappears. So because there is no symmetry anymore, the motion becomes almost seemingly random. It passes through the center, and then what is it? I can't even tell what the curve is. I don't think it's very repetitive. And the only difference is that one of the springs is stronger than the other. And so they don't work in unison anymore, and as you can see, the patterns disappear. So it kind of oscillates. It doesn't run away, because if you go too far away, you will be pulled back. And so it does come back all the time, and it has to oscillate. But now, look at this. Man, I can't even tell what this is. Well, anyway, so enough with demonstrations. So you can see how understanding of the physics of the setup is the key, because that mathematical part is really not hard. The mathematical part that is hard is how to solve this problem explicitly, the way Newton did. So he had formulas that work all the time. So this one, you see, it only describes one particular situation. So this particular initial location, this particular initial velocity, and then if we know those, well, we can see what's happening. But an explicit formula gives you all possible location, all possible initial velocities, as well as maybe other possibilities. So you can actually see long time patterns, maybe some asymptotic behavior. You can analytically look into those formulas, and there is no formula. This is a formula. This is a recursive formula. Remember, so if you know the current state of affairs, then you know the next one. But you cannot project into the future. So you can see it, but you can only examine one situation at a time, which is that is the limitation of all kinds of numerical analysis like this. So that's a challenge to solve the problem in an explicit way. So we don't. So then we turn away from simulations to another model, but this time it is solvable, and the model is about let's say it is about population growth. Okay, so population growth / decline, and since this is mathematics, well, population doesn't have to be really population. So it could be population of anything you can think of. So it could be people, it could be rabbits to begin with, and secondly, and more profound would be say money. Okay, so compounded interest. That's what happens. So once again, people or animals, money, and the third one is radioactive elements. Okay, so they all behave in a similar fashion. Even though the money is decreasing, the people could go up or down, depending on whether you have more people being born than dying. Okay, so up or down. Money is, if you put it in the bank, you pay the interest and compound interest, so there will be growth. Radioactive elements are the amount of a particular radioactive element in a plant. For example, once the plant is cut, it is going down. All the behaviors are exponential, but before doing actual exponentials, let's look at how it develops in a discrete way, because if it is about money or even people or bacteria maybe, it only happens one at a time or several at a time, but the growth is not continuous, so it will be growing like this. So ultimately the model is this. The model is a continuous curve, which what we have been doing in calculus, only making once in a while making stops to see the something else, like the simulation, which are numerical. But generally, this is the way we do it, and ultimately, everything we encounter, we want to reduce to actual functions that are familiar and we know how to analyze. So let's start anyway. Just look at a few situations. For example, what do I have here? Well, as a simple example, let's take a bacteria. Doubles in number every day. So you can imagine that in lifetime, or not lifetime, but rather adult life of bacteria is 1 day, and at the end of the day it divides in 2, and you have 2, and they grow again and divide in 2. Okay, so then if you start with 100, or say let's start with 10, and then you go on 20, 40, 80. Okay, so you can then, as we have, I guess I forgot to remind you about all these simulation. What we're actually talking about are sequences. So the fact that we started with sequences early on allows us to treat simulations properly, not like a continuous function that has been sort of sampled. So we are moving this way. It is a possibility to move like this. You have a curve and then you put dots on it, and that creates a simulation. It is not a simulation. It is a discretization of the problem that have been solved already. But once again, the main difference is these are continuous functions, and these are sequences. Okay, so if you understand the setup correctly. And at this time, none of these actually is about, strictly speaking, about physics. So there are no forces, nothing like that. There's just a pattern of development. But initially, once again, look at it. This is recursive again. So say we have a sequence, and so an plus 1 is equal to an times 2. Okay, so it is called, as you might remember, exponential growth. Exponential or geometric. Both of them. Well, unfortunately, the word exponential growth has been abused, and in everyday life, it means to people that it's just growing faster. Even though it doesn't really have to grow fast. It is a particular pattern of growth, and the exponential growth could start slow. It could say, if you have, I imagine that your interest rate, your APR is say 5%. 5% in your bank. You do have exponential growth literally by definition, but you simply multiply every years, for example, by 1.05. Is it really that fast? That certainly doesn't look fast. And even if you take 2 years, it's still not a lot. It's not going to be a lot. So it starts slow. It could be slower than other patterns of growth. So we certainly obviously outside of the classroom, you don't really have a choice of how you understand people using the word, and then you might have to use it the same way. But certainly in a mathematical or a science environment, the exponential growth has a particular meaning. Okay, so if we move on from this recursive formula, which is good, but the problem with recursive formula, as I mentioned just recently, that you cannot progress into the future. You can only proceed one step at a time, and you hope you carry out enough iterations to see what has happened. But we want more, and so we make this conversion over here from discrete to continuous, and the idea is so doubles every day, or it doesn't have to double. whatever the proportion is, the growth rate is proportional to the population. Okay, so that is how we describe it. Observe that this is kind of similar to what we just did, the verbal description, which might seem imprecise, but we just did this a few minutes ago with the spring. So we need the force was proportional to the to what? The state of affairs. So the state where our position was, there is no physical position here to speak, so we can speak of that. But if in either case, we can speak of the state. So the state in that physics simulation was our location, and here the state is the population, the number of say bacteria at that moment. And then the number of bacteria determines the rate of growth. Right? So for example, if you have 10, you will have 10 you add 10 the next time. That is the growth. But if you have 20, the growth will be by 20. So that's the proportionality. And so once again, with the interest rate, if you have 5% interest rate, it seems like it's the same. But if you have $1,000, the growth will be by 50. But if you have 1 million, the growth will be by 50,000. So once again, the growth is proportional to the population, whether it is bacteria or money. Okay, so then what we end up doing is just like yesterday, we write our differential equation based on this. So suppose the function that we're talking about is some function y equal y of x, and then we say the growth rate of this quantity as a function of x being time. So this is the quantity, and x is time. So then what I say here is dy dx is equal to, it is proportional to, say, 2, well, let's just say constant times y. This is the differential equation describing the population growth. Population growth, once again, whatever this is. So this time we have made this transition from discrete, right there, to continuous, because now we're speaking of function y equal level x, which is defined for every x, and then the growth will be continuous. It will be a curve like this. So no missing points, which seems like we make things more complicated, but really we do not, provided we can solve the differential equation. Okay, so let's solve it. So can you solve it? So, well, think about it. The derivative of the function is equal to the function itself multiplied by a constant number. How about c is equal to 1? So y prime is equal to y. What kind of function, when differentiated, gives the function itself? What?
Is it an integral?
No, the integral. The problem, we cannot integrate it. We cannot integrate it because the left hand side depends on x, but so I mean, if you try to integrate, so suppose integrate, this is what I'm going to have. Integrate y prime dx is equal to integral y dx. Okay. So, okay, well, let's do it since it came up. What happens to the left-hand side? This is, I wonder if you remember what this is equal to. If you integrate the derivative, what do you get?
Is that going to be y?
It will be y, as a matter of fact, yes. It will be y. So it might appear that we have solved the problem, but look at what we've got. This is what we've got. We still don't know what this integral of y is. Why? We cannot integrate y until we know it. So since we don't know it, not only the left-hand side is unknown, the right-hand side remains unknown too. So that's the problem with differential equations, is that they cannot be solved by integration. So just to point out the difference again, if I have y prime is equal to, say, x squared, right? The right-hand side depends on x. So when I integrate in the same manner, I have y or y prime dx is equal to x squared over 3 plus c, right? Not too bad, and then this is y. The left-hand side, the same thing happens to the left-hand side, and the problem is solved, right? So it's kind of similar, but once again, look at it. This one, the equation that we're looking at, this one in particular, has only unknown y on the right. If the right-hand side of the equation was a function of x explicit, then there is no trouble solving it, as you can see, but that's not the case. That's the challenge with differential equations. So the only way, for the time being, to solve such an equation is to, well, remember doing differentiation many times and seeing some patterns. So once again, you differentiate a function, you end up with the function itself. You may have done it a few times. Well, it is a familiar function. That's the hint. A familiar function equal to its own derivative. No? You look at the list of derivatives. It's not a long list. You know, it's like less than 10. Well, I just wonder if, can Google answer it? I wonder if, so do Google search. So, how should I say? Function equal to its derivative. Okay, see, there is a choice. Function equal to its derivative. Should I click, or do you remember? Now you remember? Function is equal to its own derivative. So that's a lot of lectures or links. Yeah, so the exponential function is the answer. The exponential function, base e especially, not only that's what I certainly expect you to remember. This one I do expect you to remember, and we're getting closer and closer to the final, and so some of you got to start remembering formulas. So the exponential function is what to remember is the function that is equal to its own derivative. So that simplest version of our differential equation at the top, the one in green now, it has one solution. It is either exponential function or exponential function with a coefficient. So say k. Well, I don't like k. How about a e x? Okay, so if I differentiate it, I use the constant multiple rule. So this is y prime is this. I differentiate by constant multiple rule. I have ex prime, and I have a ex, which is y. Okay, so there is really no method here, but nothing but just memory. But I mean, like I said, there are very few formulas that we have to face right now. Okay, so the problem is solved, and that is actually, I think, named after Euler, I think. So it doesn't stand for exponential, I think. And then so that gives me one solution. Then what remains is so I want the general solution. So we solved one problem, then we know where to look now. We know where to look. Now I want to solve the other one, the general one. So can you think of that? So y prime is equal to cy. So there is an extra coefficient. So where that c would come from? So it will be kind of exponential function, but with an extra coefficient. So under what circumstances an extra coefficient would appear? When you differentiate, you're going to differentiate. So once again, like this, you differentiate, what do you get? Where do coefficient appear when you differentiate? Constant multiple rule, but there is another possibility. Well, the chain rule. The chain rule creates a coefficient. Well, if you remember, let me say A, E, Cx. Let's differentiate. Once again, constant multiple rule. A, E, Cx. What's the derivative? ECX by the chain rule. C to the x, yes. Okay, so that works out, as you can see. Yeah. Okay. So so indeed that coefficient that appears to be a coefficient, actually where it comes from the exponent, and that is the where that the whole thing is located, where it makes things grow, as well as increase or decrease depending on that number in the exponent. C will give us either decrease or increase of our situation, and once again it could be population. Then there are more deaths outnumber births, then there will be decline of the population according to the same rule, according to exactly the same rule, because you know it's still proportional to the population. The likelihood you can have either like 50 babies per 1,000 population, or you have 50 deaths or 60 deaths per 1,000 population, and then you will see that there will be, it's just life. People get old, and then you will have a decline if you don't have enough births. Okay, so and then so that's pretty much the whole thing. So the general exponential function is that, say, A, E, C, X. A is just a coefficient, meaning that this is like the initial state or initial population, and C the growth or the decay constant. Okay? Indeed, if I plug in x equals 0, so f of 0 is a e 0 times x, or a. Okay, so it's like your initial investment, possibly. So just what we know about the exponential functions, let me refresh your memory. So assuming that a is positive, then what's going to happen, it's depending on the value of c, we either have the growth or decay. So this is c positive. Okay, the larger the c is, the faster it's growing. This is the x-intercept is a, and hypothetically we have c is negative. We have a decay with in either case we have an asymptote, either on the left or on the right. So this is c is negative. Naturally, c is equal to 0. You have a constant function. Okay, so these are models are interesting, but really they are only interesting because of the situation that you look at, and the population, or it is either people or money or bacteria, and something else that for us to explore would be is to especially for the population, there is a limit. There is always a limit to how far it can go. Either the bacteria is growing in a like a glass piece of whatever it's called, some kind of in the petri. Yeah, I guess, yeah, petri dish. That's right. And they grow fast at first, and then they start slowing down because they run out of room or they run out of food. Well, the food is, so if you feed them a particular amount, then they will be once again growing fast until their food becomes scarce more, and then only part of the population will be growing, and that is the extra condition that comes into play in order, and we have to modify the model. But the interesting scientifically topic that doesn't require anything extra is this. Radioactive decay and radiocarbon dating. You know what it is? Radiocarbon dating? That is really interesting. So, or is just simply carbon dating? So there is a particular radioactive element, say, what is that, the name I can never certainly remember, carbon-14. Okay, so the amount is constant. In a plant. Okay, but when it's alive, when it's cut, it's dead, it starts to decay exponentially. The coefficient, so it will be then A, E, C, X, and C is negative. So that will be the amount, f of x, the amount of that particular carbon radioactive element, and will be decaying exponentially. So what is it good for? Really? Never heard of it? Dating fossils, yeah, fossils or anything. How about paintings? Because they use plant-based paint often, and then going through this, you can figure out when the tree was cut. Okay, so, or if it is a piece of cloth, that was a shroud of Turin, you might remember, that's how they tried to carbon date it. So because once again there is some of the material was made of plants, so you take a piece of it, doesn't matter how large it is, how small it is, you know what it is, and you can figure out the decay coefficient is the key. If you know what that radioactive element is, you know how fast it decreases. So you know C. If you know C, you have this whole picture available, and it is proportional. It is proportional, so you can do it on a small piece or a large piece. It doesn't matter. You know that for this mass of this material, you're supposed to have you had initially this much proportion of amount of radioactive material, and now you have only half. So you had 1 milligram for, well, it's not a milligram, it's less than that, and now you have 1/2. So what has happened is it lost half of it. Okay, that's called half-life. As you can see, look at the picture, it never loses everything. That's why to measure or kind of estimate or just give you an idea how fast it is decreasing in weight, give you the half-life, which is frequently like 5,000 years, because it will never totally disappear. So this is, for example, is 1, and this is 1/2. How long? Well, carbon-14 is 5,730 years. Okay, so once again, if you expect to have 1 milligram and you see in the material half of it, it means that it has been 550,730 years since the tree was cut. And then, but you realize that if from that number you can figure out C, from this number you figure out C, from C you figure out the function, so knowing one number gives you the whole curve. So it means that it doesn't have to be half that you lost. If you lost, well, okay. So if I have 1/4, how long has it been?
Double the time.
That's right, double time. Yeah, because it's 1/2 times 1/2. So you twice lost 1/2. That's how you get 1/4. So it's 5730 times 2. That's how long it has been. Okay, so well, this is probably less likely. But if you're dating anything more recent, you can still do it. So if you lost only 90% of the material, it means that it has happened more recently, and you can find that number from that formula. Okay, so certainly to establishing these connections, you gotta know logarithms, and so let me just go through one example. So what I have here is, so half-life is 5,730 years, okay, and we have a parchment that is 74% of carbon-14 left. So how old is it? Okay, so intentionally chosen, the number is chosen in such a way that you cannot reduce it to repeated application of the half-life. Okay, 74%, even though it appears to be, actually 74% is close to 1/4. So it will be close to 5,700 years, but let's say we want something more precise. Then so let's go through these computations. So the formula is here. So we need to find this is a C. We need to find C. So we could assume A equal to 1. That doesn't matter because we are doing percentages anyway. So we need to find C from this formula, and this is how it works out. So it is 1/2. So I'm using half-life, 5730. 1/2 is equal to 1 times E C 5730. Okay. So the x is equal to 5730, the length of time since, and this is the drop from 1 to 1/2. Okay, so from here you can find, well, how do we find how do we find C? Say it again.
Not very good with log, but I think it would turn out to be log base E of C and then separated.
Well, yeah. So use the logarithm, right? So the every time you see a formula with the exponent of base E, you apply logarithm base E to both sides. Okay, so apply ln. Okay, so natural logarithm base E. And so if two things are equal to each other, then so are they logarithms. Because logarithm is such a function that, well, if you remember what kind of function that is, well, maybe we'll talk about that at some point. Okay, and then what happens on right, we can simplify it, right? So what happens?
The log and the E cancel out.
Yeah, so what's left?
C times 57.
C times 5730, right? So, and then C is equal to 57, ln 1/2 divided by 5730 to be computed with a calculator. Okay, so if you have this, then you can just, I actually have a number here somewhere. Or maybe not. So anyway, the point now, we know what our exponential function is. 1c is identified, right? So all we have to do is just to plug in the 74 into this formula. So first of all, f of x is equal to then e. Well, I don't really want to repeat this number. It will be cx with c known, okay? And then if we are left with 74%, then this is what we have. We have ECX equal to, now x is unknown, 0.74. Okay? So we had 1, the initial amount. We're left with 0.74 over the time x that is unknown. It is exactly what we're supposed to find, the value of x. And then the solution is once again the same. We apply ln, and what I have, ln 0.74 is equal to cx. So x is equal to then ln 0.74 divided by c, which is that number that we found, ln 0.74 divided by ln 1/2, and this becomes the numerator. Okay, so the answer I have here are roughly 2455. So what I said was so 74% is left. So that's I misunderstood it first. It is 74% is left, which means that it's not the same as 75% is lost. 75% is lost is this. This is the case of 75% lost, and you're left with 1/4. So then it is like a 57, 30 times 2. Going the opposite direction will be roughly half. You can, if you are doing like a inside your head computation quickly, then if you know that 75% is left, then you roughly take 57/30 and divide by 2, right? So that would be produce 28/15 or 28/65, right? But that's an approximation, only done very quickly. The more accurate computation is this, as we did it. Okay, so we'll do a little bit more of this next time.